I am Dan Gaude, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss variational principle from the classical mechanics of MSc first and semester first. Theorem for variational principle, basic theorem, fundamental theorem. Now see here. Find the Euler Lagrange differential equation satisfied by twice differentiable function y of x, which extremizes the functional y of x is equal to integral from x1 to x2 f of x y dash dx, where y is prescribed at the endpoints. Consider xy coordinate system and take in xy positive quadrant 2 points P and xq, coordinate of P x1 y1 and coordinate of Q x2 y2. Joined PQ straight and core and core, draw the core PQ. Let P of x1 y1 and Q of x2 y2 be two fixed points in xy plane. Then the point P and Q can be joined by infinite similar mini curves according to the value of the integral I will be different for different paths. We shall look for a curve along which the functional I shall look for a curve. Let's see with the curve between P and Q, whose equation is given by y is equal to y of x0. Let also the value of the functional along the curve C be extremum and is given by I y of x is equal to integral from x1 to x2 f of x y dash dx. We can label all possible paths starting from P and ending at Q by the equation y of x alpha is equal to y of x0 plus alpha eta of x, where alpha is a parameter and eta of x is any differentiable functions of x. For different values of alpha, we get the different curves according to the value of the integral I will be different for different paths. Since y is prescribed at the endpoints, this implies that there is no variation in y at endpoints. All the codes of the family of must be identical at fixed point P and Q. That is, eta of x1 is equal to eta of x2 is equal to 0. Conversely, the condition eta of x1 is equal to eta of x2 is equal to 0 ensures that the curves of the family that all pass through the points P and Q. Let the value of functional along the neighboring curve be given by I y of x alpha is equal to integral from x1 to x2 f of x y of x alpha y dash of x alpha dx. From the differential calculus, we know the I is extremum if del by alpha at alpha is equal to 0 is equal to 0. Since for alpha is equal to 0, the neighboring curve coincides with the curve which gives extremum value of I. Thus, del by alpha with at alpha is equal to 0 is equal to 0. That is integral from x1 to x2 del by f by del by y eta of x plus del by y dash del by f by del by y dash eta dash of x dx is equal to 0. Integrating the second integration by parts del by f by del by y dash eta dash of x integrating and same as it is. Then del by f by del by y dash eta of x from x1 to x2 minus x integral from x1 to x2 d by dx of del by f by del by y dash eta of x dx is equal to 0. Y is prescribed at the endpoint, therefore eta of x1 is equal to eta of x2 is equal to 0. Therefore, integral x1 to x2 del by f by del by y eta of x dx minus integral from x1 to x2 d by dx of del by f by del by y dash eta of x dx is equal to 0. Combining this, integral from x1 to x2 del by f by del by y minus d by dx of del by y del by f by del by y dash eta of x dx is equal to 0. Using the basic lemma of calculus of variations, therefore del by f by del by y minus d by dx of del by f by del by y dash is equal to 0. This is required Euler's Lagrange's differential equation to be satisfied by y of x, for which the functional I has extremum value. It is note that eta of x from x1 to x2 is not equal to 0. That is, eta of x1 is equal to not 0 and eta of x2 is not equal to 0. The value of the functional I is taken only on the extremal between 2 points, and hence we must have the Euler's Lagrange's equation is true. Consequently, in this case, we must have from equations del by f by del by y dash from x1 to x2 is equal to 0, and del by f by this implies that del by f by del by y dash at x1 is equal to 0 and del by f by del by y dash at x2 is equal to 0. And now see here proof of the Euler's Lagrange's differential equations and so on. Now see here. Next, generalization theorem for Euler's Lagrange's differential equation for several dependent variables. Theorem now see here. Derive the Euler's Lagrange's equation that are to be satisfied by twice differentiable function y1 y2 dot dot yn that extremizes the integral I is equal to x integral from x1 to x2 f of x y1 y2 dot dot yn y1 dash y2 dash 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 yn dash dx subject to the condition y1 y2 dot dot yn, which as you described at the x fixed points x1 and x2 and so on. This is one example related to the variational principle. Show that geodesic nothing but shortest distance between 2 points in a Euclidean plane is a straight line. Take any 2 points in a plane. That points should be fixed. That is, suppose that P and Q, P of x1 y1 and Q of x2 y2. And suppose this point P from Q, there is a curve y is equal to f of x, and by the distance formula ds square is equal to dx square plus dy square. Hence the total distance from P and Q along the curve is given by I integral from P to Q ds. In terms of x is the independent variable, y is the dependent variable, therefore y is equal to integral from x1 to x2 1 plus y dash square raised to half dx, where y dash is equal to dy by dx. Here the functional I is extremum if the integrand f is equal to 1 plus y dash square raised to half must satisfy Euler's Lagrange's differential equations. That is dou f by dou y minus d by dx of del by f by del by y dash is equal to 0. Here f is equal to 1 plus y dash bracket square raised to half. Therefore del by f by del by y is equal to 0 and del by f by del by y dash is equal to y dash divided by square root of 1 plus y dash. Therefore d by dx of del by f by del by y dash, again it is 0, and this is y dash is equal to c square root of 1 plus y dash square. Squaring on both sides, and y dash is equal to c square root of integrating, therefore y is equal to c1x plus c2. This is the form of straight line. Thus the shortest distance between 2 points in a Euclidean plane is a straight line, and hence which is required proof.